Okay, I shortened it. So this is the work we're doing under a project supported by the university, looking at air quality, particularly looking at the effects relative to the changes going on in climate, but also looking at how various assumptions one makes in emissions can affect that. And I have two students working on this project, Swarnali Sanyal and Jun Zhang. Well, thanks to the formation of EPA in 1970 and the resulting US Clean Air Act, even though we have 3 times as much fossil fuel consumption now than in the 1960s, the amount of pollution emissions have actually been reduced by over 98%. As a result, we have much cleaner cities and urban environments than we did at that time. And essentially, we're spoiled because we don't realize what impact this had. But nonetheless, we still have about 200,000 premature deaths per year in the United States as a result of air pollution, outdoor air pollution. And over 3 million premature deaths worldwide, mostly in Asia, China, and India, and related countries, which are too surprising given the air quality issues they have. The focus here will be on 2 of the primary pollutants that cause these issues. The first is ozone, which is a major health risk because of it's an irritant to the respiratory system and reduces lung function. Ozone is created in the atmosphere by various reactions. The ones most important to air quality are those involving the nitrogen oxides reacting with hydrocarbons, or what are called volatile organic compounds, to result in the formation of an oxygen atom, which then reacts with O2 to form ozone. The other big concern are particulate matter. Historically, the big concern was to look at what was called PM10, particles less than 10 microns. But those particles, the larger of those particles, only can penetrate the very top of the lungs and can't have, doesn't have, if there's too many of them, it can cause a very serious health issue, as we've had in the past with cities affected by soot, famous one being in London in the turn of the century. The big concern now is what's called PM 2.5. Those are particles less than 2.5 microns because they can penetrate much deeper into the lungs. And those can be created both externally, but also particularly through gases reacting in the atmosphere that then become particles. Now, one of the big concerns here is what is the impact of changes in climate relating to this? Certainly we know emissions are very important, but also the outward climate is also very important. Warmer temperatures lead to more ozone production, well known. Increasing concern about wildfires as the climate is changing, increases both ozone and particulate matter. Drier soils results in more dust storms. We're actually seeing the effects of that already. Results of long-range transport. Pollutants from Asia are already affecting the United States air quality, but also countries closer to us, from Mexico and Canada. Shifts in weather regimes, like the changes in the jet streams, affect what areas are likely to be polluted. Changes in Bermuda High and how that affects pollution, particularly on the eastern part of the United States, and other aspects, storm activity, et cetera. This project is aimed at enhancing our understanding of how air quality in the United States could evolve in the future with changing emissions, emission sources under a changing climate, going beyond all the previous studies that have looked at some of these issues, by really trying to go into much more detail of understanding the episodes and what is behind them. What are the major causes of the major episodes we see now? And provide actionable information for designing effective air quality management strategies that can help policymakers. The project design is the focus on air quality over sensitive areas in the United States, so we particularly focus on some particular regions, with where there are high probabilities about PM 2.5 and ozone exceeding the national air quality standards that have been issues in the past and are likely to be anticipated to be issues in the future. And including, all these kind of concerns I mentioned in the previous slide. We do this through what we call the dynamic prediction system, where we use a combination of a global model, which is what I'm going to mostly talk about today, regional climate model, and then coordinating that with the EPA's air quality model. And so coordinating all of these activities where the global model feeds in the boundary conditions for the regional model, and the regional model then feeds in the climate that feeds into the air quality model. The global model is also determining air quality, it's just not as high a resolution as we're going to do with the air quality model. We're going to do on the order of 1 degree, about 100-kilometer resolution for most of the cases, but because we can use blue waters, we're also going to be using 0.25 degrees, which gets us to 25-kilometer resolution, feeding into the regional model, which is going to be run at a resolution of 10 kilometers as opposed to previous studies mostly being at 30 kilometers, and likewise the air quality model being run at 10 kilometers. There's lots of aspects to this. One has to be very careful how one handles the emissions, and so there's lots of details I'm going to skip over today. So we're going to apply this dynamic prediction system to determine individual and combined effects of global climate and emissions to look at air quality in the US, so that we can then pinpoint what's causing various effects in various regions. Result is to quantify pollution sources and assign their attribution, natural and anthropogenic emissions, national versus international effects, long-range transport effects, and natural variations versus climate change effects. And determine a timeline for the global change factors to become significant so that one can take effective actions. On blue waters, we're doing a whole series of historical simulations and future projections. I've already mentioned the roughly 1 degree calculations, and then a 1/4 degree being done with the global model. And then with seawharf, likewise, we'll do historical and future simulations at 10-kilometer resolution, and then the same with CMAC to get at the air quality from that model. The global model has fully coupled climate and chemistry included. So why blue waters? Blue waters enables us to the kind of high-resolution simulations we're doing here, both with the global climate system and then which has fully coupled chemistry, and also the sensitivity and case studies that can be done with the full dynamic prediction system that couples the global model with the regional modeling studies, and looking at all these different questions that I've already raised. Well, we already know from past studies that there's, and this is based off a study we've published recently, the relative factors that contribute to ozone and PM 2.5 are greatly affected by emissions. So as you reduce emissions, you can certainly reduce the air quality concerns. That's a big effect. But as you increase it depends on what assumptions one makes. So if one looks at a high emissions scenario, which is the red here, that's assuming a continued heavily use of fossil fuels, in which case air quality is going to likely to get much worse, both because of the emissions changes, but also because of the climate changes. Whereas if one goes to a lower emissions case, which is RCP 4.5, the green, then the emissions are significantly reduced, but climate change is still going to take one in the direction of tending to increase the resulting air quality. Long-range transport is again likely to be worse than the high case. That depends a lot on how other nations do handle things. And then the other aspect of this is model design. How much does treatment of clouds and other parameters in the model affect the resulting air quality? And that can go in either direction, and one of the things we'll be doing is trying to better understand some of those effects of the model itself. What's on the right-hand side here is just showing the effect of the scenarios, those RCP scenarios on global temperature. And you can see in the high case where we look at continued heavy use of fossil fuels, we could see 8 to 10 degree increases in temperature over the end of this, by the end of the century. And right now, that's the scenario we're best following. We hope to get down to the RC 4.5 scenario, which is the one in dark blue, where, I'm sorry, it's lighter blue. The lighter blue is the 4.5, and that's, we get down to 3 to 4 degrees. If we can pull off the Paris Agreement into its full extent, then we can maybe get this down to 2 degrees. But that's going to require nations really strongly abiding by that. Based on past studies, we also know that ozone surface concentration under different climate scenarios can greatly change. Looking at a low emissions case here relative to a baseline of relative to 2000, looking at mid-century with the low emissions case, generally over the US you see a significant reduction in total effect because of the significant reduction in emissions, even though there still is a climate effect that would tend to make things worse. On the other hand, if we look at a high emissions case, then air quality throughout the world tends to get much worse, including in the United States. I mentioned wildfires earlier. One of the new factors that, or one of the factors that we've actually recognized for some time but haven't really accounted for in these kind of studies is that wildfires can have a significant impact on both ozone and PM 2.5. And just as an example, this is based on a study that well, this isn't our work, but we did a very similar study ourselves, but I like these plots better, that looked at a Canadian set of wildfires from a few years ago and show specifically significant effects on both ozone and PM 2.5 in the United States resulting from wildfires that occurred in Canada. We've known for a long time, this is again from a past study that my group did, where we looked at long-range transport from Asia and its effects on the United States, showing that of the ozone in the US, the effect can be 5 to 7% of the total effect. And for black carbon aerosols and PM 2.5, it can range from 0% in the eastern part of the US to a pretty high percentage of the air pollutants on the West Coast. Other studies have shown that you also get a significant amount of increase in dust that is affecting the US, that the inflow of dust from Asia and in other parts of the world can be essentially as large a contributor to PM as what we're producing here in the United States. Now, I mentioned the air quality standards. These just give you the numbers. For example, ozone, a daily 8-hour maximum of 70 parts per billion, and various levels of PM 2.5 to consider. We've done some new analysis. This is based off the Blue Waters runs. This just looks at the EPA system of observations across the United States for ozone on the left and PM 2.5 on the right. And then the bottom shows that the number of times that various sites have had violations on particular years. And we're just going to focus in on 2005, where we did some analyses recently. And when we look at that, the left shows the upper left is the ozone production going through 2005, month by month, I think it is. And the bottom is the PM 2.5. These are all runs from CMAQ, from the air quality model, EPA's air quality model that we did. And then the right shows the violations. And you see significant areas of violations, particularly in Southern California, for example, was long known to be a serious problem. And for this particular year, the matchup with the numbers is pretty close. It's not exact, but it's quite good. One of the things we did discover for this year is also that through the combination of having the global model feeding into the regional model, is that high Canada and Mexico emissions near the US borders also affected the amount of PM 2.5 and ozone violations in particular regions. A new result is looking at just the global model and showing the changes in ozone concentration and PM 2.5 across the planet based on the model and how transport of ozone and PM is extremely important, as well as local production. So in summary, our global and regional model simulations are currently underway and are being used to evaluate the factors affecting past and projected high pollution events in the United States for both ozone and PM 2.5. The dynamic prediction system is to be used then to enhance scientific understanding of the impacts from global climate and emission changes and effects of long-range transport on US air quality management, so that we can separate out the effects of what changes in emissions have versus changes in the climate system and changes in things like long-range transport. Finally, a whole series of sensitivity and case studies analyses are being done using this system to evaluate potential impacts of various pollution sources on future air quality in the United States. Thank you.